Hello, everyone. Very happy to be here. So you have here my presentation plan. I prepared some very holistic content on energy transition narratives, a call for more coherence, because honestly, I don't see a transition so far, just addition, adding new forms of energy and demand. Then I have a few slides on the mining industry, because energy transition, clean, renewable, energy generation technologies require a lot of metals. So we are shifting to the mining industry and its externalities. And finally, I have a few slides on net energy analysis, energy return on energy investment, life cycle assessment, the reasons why I believe it could be very good indicators to help us make better decisions in the planning of our energy future. And to finish, a few words on deep geothermal. I'm active in the deep geothermal landscape, and obviously I think, I believe it's a very promising solution. I do see great potential to change actually our energy landscape, but we should do it like very properly. Slide. So on the energy transition, it has not reversed the great acceleration so far, and I don't believe if we continue so it will ever. The very concept of the energy transition arrived back in the 70s, associated with the Club of Rome report on the limits to growth. And the global expectation was to say, okay, we are going to deploy clean energy technologies, and so this will enable continued economic growth, and we will decline the environmental impact. And the thing is, the reality is that this has not happened. So socio-economic trends continue to rise, and the Earth system trends are going on the same acceleration. We have crossed 7 of the 9 planetary boundaries. So yeah, absolute decoupling is not happening, and we need to actually a paradigm change. It's as simple as that. Now, the next slide is here on material extraction keeps growing and circularity is declining. A lot of people speak today about circular economy. Okay, so yeah, we need always more, but we are going to recycle everything, and so we will be fine. This is an illustration taken out from the Circularity Gap report, showing the annual material flow in the global economy. And what we see is that, okay, it was in 2022, so 100 gigaton of material extracted, biomass, minerals, fossil fuels, ores, and getting processed in the economy. And at the end, we have 61 gigaton that are simply lost. It's dispersed, it's emitted, or it's trashed away. 31 adding to the pile of what we already have, the technosphere, and 8.6 gigaton actually being recycled. And what is very worrying is that the ratio is getting down. So we are extracting faster and faster and recycling proportionally less and less, because we cannot follow the pace. And one of the worrying segment is also the electronic waste. This is the fastest growing segment of waste globally. And because the material that we create are getting more and more sophisticated, the mixtures and everything, so the alloy is going very complex, it's getting almost for some impossible to recycle things on your smartphones or this stuff. And globally, less than 20% are formally collected of this electronic waste, and it's collected. It doesn't even mean that it's recycled. So there is really a big issue. And now this is an illustration I really love. It shows that all previous civilizations have been built using just 7 metals, the one that were available on native forms. And then with the Industrial Revolution, we got access to more energy, so we were able to extract more and more. Also, metals that are not available in native form, like silicon, that you always have to separate. And in the 70s, we still had less than 20 metals in the global economy. And with that, we have been able to send a man on the moon, which I think is already quite amazing. But then after the 70s happened something very weird. We speak about dematerializing society, getting on the internet, digital, think on the cloud, AI. It feels very unmaterial, but it requires the full table of the periodical table of the elements. And this comes with very big challenges, socio-environmental challenges, because on an energy point of view, the grades of the ores that we mine are getting down. So we need more and more energy to extract the materials. And the energy for the mining industry is fossil fuels. It's oil, coal, gas. We are not mining with renewable. And then on the pollution side, the mining industry by essence is the most polluting one, because we extract material in part per million, part per billion. So all the rest, 99.999, is waste. And it comes in very reactive forms, like its tailings that are very reactive with airs and contain toxic materials. And there is nothing we can do about cleaning a mining site. You can cover it. This is sometimes done. You can displace, but nothing else. You have this for millennium to come. Deal with it. Now, on social justice, that's the last point. The mining industry is very predatory, and this is the topic of the next slide. So this is excerpted from the Global Atlas of Environmental Justice, where they monitor the environmental conflicts worldwide, and what they see is that the mining sector, followed by the energy and climate sector, are the leading sector in socio-environmental conflicts. And the mining is also the one where you have the most it's the deadliest for activists, so the most assassination happening related to activism trying to defend. So the key causes on that is actually the unequal distribution of profits and externalities. And so I think this is also something that we can think on how to redistribute. It's not about closing all the mines, but it's about being more just in the way we do these things. So the whole point is to say that the technology choices that we make today is shaping the demand of the future mining industry. And on the left side, these are data that were provided by a university in Europe. They investigated how much metal are required to make a free, carbon neutral Europe, so according to the Paris Agreement. And they looked at all the metals, excluded the steel, because this is a few order of magnitude above. But what they see is that it's a 10-fold increase. And this is dramatically big, and it comes in a context where every other sector is also on this great acceleration. If you think on data centers, but also efficient building requires a lot of metals. Look around us, and so how do we manage this? Defense also is another sector that is also demanding a lot more metals. And on the right side, what I also really like this diagram, it comes from an association, non-for-profit from France called Systext, where they look at the externalities of the mining industry. And they looked here at the elements required for clean energy generation technologies. And what I think is very fascinating here is to see that geothermal is actually very low tech. Nuclear is on the high end, requires a lot of different metals, but geothermal is actually just circulating water in pipes, and that's it. Now, the point here, the trick is that it has been built looking at conventional geothermal, and probably we will have to investigate what next generation, so super hot rock, advanced, enhanced geothermal system require in terms of deep drilling and so on. But I think for geothermal, it's like very promising. It's a big consumer of steel, but steel is not critical. It could be locally produced and also have a better like monitoring of the supply chain and provide like local revitalize local industry. So yeah. So I think the whole thing here is like to say that something that has been very much overlooked in this energy transition strategy that we have is this energy resource trap. So the integrated assessment model that are typically used by governments to create the energy transition scenarios, they are not looking at energy balances, at material flows, at resource quality availabilities. It's like you said, it's like, okay, we want to be there by 2050, but no idea how it's going. It's just going to happen. And one of the things, so some researchers and academics have started looking into this energy resource trap. I think in the literature it's more called energy emission trap. And it's really the fact that what we are willing to do is deploying massively new renewable energy technologies. And so we need more metals. And the metals that we extract are getting less and less concentrated. So we need more and more energy to extract them. And the relationship here is exponential. And to extract minerals or mine, it's only fossil fuels. And fossil fuels are also getting more difficult to extract. I think on non-conventional, offshore, tar sands here, shale oil, very energy intensive process. And all this is to create infrastructure that require more metals per megawatt hour produced. And so what this researcher looked, so this paper, they show that if we go for it, the risk is actually that we will decrease net energy available to society and generate like socioeconomic crisis. Not mentioning also all the dependency on mining and all the environmental problems associated with it. So this is where I think we should really look at this energy return on energy invested metric. It has been around for quite some times, but I think there is a real job of harmonizing the procedure and being more clear where is it evaluated, because typically in the literature you will find energy system evaluated at the extraction stage, like at the wellhead for oil and gas, or at the distribution, or at the point of use, or that would be the plug for a solar panel or so on. And so it's very difficult to harmonize and make sure that we are able to compare apple to apples. Life cycle assessment has been around and is already pretty well known, but it's not mandatory, and I also think it should be, and also very well aligned and make sure that everyone use the same system boundaries. And here again, it's around for geothermal for conventional, but it's non-existent for enhanced and advanced. And so I think really there is an effort from the community to do and get these tools ready. And now finally, this is a graphic I really like. It's the net energy cliff diagram that shows from energy return on energy invested, like you have on the, how can I explain when I'm not in front of the... So the horizontal axis shows you the energy return on energy invested. On the left side, you have the high energy return. And so for this, you see on the vertical axis that almost all the energy is available to society. So of course, this is the kind of system that you would like to have, because the real question behind is like what's the minimum energy return on energy invested that we need to sustain our modern economies, because we need more energy to do stuff afterwards. It's just not for getting energy. And what we see is like for oil and gas, the conventional oil and gas is getting down. I didn't even indicate non-conventional, but non-conventional oil and gas is at 2 to 4, like tar sands. So it's very low. It's extremely energy intensive and not sure it can provide sufficient level of energy to sustain the economy. It's just like, because at the moment we still have a lot of conventional in the market, and this gives us some space. Now on new renewable, what I think is very interesting is that it's dynamic, because it's renewable source of energy. So if the system is well dimensioned for many, many years, we may be able to climb above the cliff, like bringing systems that produce more and more energy for a very long time. And I think this is very valid for geothermal, because geothermal can be dimensioned to last for decades, if not, I would say, century. And so, yeah, this is actually why I'm still here. After reading all this very depressing stuff and material, I still believe that geothermal has something to bring into the game, really, because it's decentralized, it's local. I mean, everyone in this room knows that it's different. I mean, you cannot, also what I really like, it's like a short travel energy. It doesn't make any sense to trade geothermal. So it could completely transform the geopolitical landscape by providing like autonomous energy communities. Then it's, again, terms of understanding what is a community, how big, how large, and so on. And one of the aspects I really like also, it's that it's the only tangible solution for oil and gas to actually repurpose, transfer their activities in a new renewable space. And to finalize, so this is like a private joke, but we had the Atoms for Peace back in the 50s or after Second World War. And we see this great acceleration, adding new forms of energy, speaking about sustainable development, but not really happened. But actually geothermal could start replacing for real, shifting, phasing away oil and gas by bringing a new energy in the mix, using the same tool, and yeah, making a better future. And I think I will stop here. Thank you. This is another image I like.